Let's see, what were we doing? We were looking at reactions last time. So we left off with one of these. I think we've just done the cyanide one. So potassium cyanide, what type of reagent is that? Well, it's charged. The potassium's the plus part. And this is primary. So what type of product do we expect here? Hopefully you can begin to see these pretty clearly. We'd replace the chloride with the cyanide. Okay, so SN2 reaction, leaving group, chloride's a good leaving group, and that would be the product with the cyanide. Carbon-nitrogen triple bond and a lone pair on this nitrogen back here. But if you draw out the whole thing here, you got the triple bond and a lone pair there, and there's a negative charge now on that carbon. So that's a good nucleophile, we say. And then what about this? This is an acetylene anion, triple bond, and we've deprotonated. We've taken the proton on this N carbon, the acetylene off. And this is a sodium salt of that. These can be made, okay? And if we react that with this propyl chloride, what do we get? We get a new bond right here. And sometimes that's good. Analyze where the new bond is being made there. So we make a new acetylene compound. The anion displaced the chloride, which was right there, and we create that product right there. Okay, now we can propose some other types of reactions. How good of a leaving group is hydroxide? Okay, and we've got amide anion here. Is this reaction going to be successful as I've drawn it right there? Is there something else that's just going to occur here that's not going to be a substitution? What do we know about amide anion? Is that a strong base, a weak base, not a base? What is it? Comes from ammonia. The pK of ammonia is 38. So what would you say? That's a very high number. So the conjugate base of ammonia is what? A very strong base, right? So, and you might think, well, that would make it a good nucleophile. And indeed, nucleophilicity, the power to act as a nucleophile, does parallel basicity. And you might say, well, how good of a leaving group is this hydroxide? Well, we also have what? H here, right? That's a weak acid, but strong enough to simply get deprotonated there, okay? So the product here wouldn't be substitution. It would simply be the deprotonated alkoxide plus ammonia, NH3. So be careful here. This is a poor leaving group, and this is a very basic reagent. We generally want nucleophiles that are not too basic. In fact, the optimal pKa range for their conjugate acids is about 5 to 15. If we get too far above that, like this one, 38, okay, that means it's just going to deprotonate something. And plus, this is a terrible leaving group. Why is that a bad leaving group? Why do we not get this plus hydroxide coming off? Well, here we're creating another strong base, okay? So this carbon-oxygen bond does not function as a leaving group to form hydroxide here. Again, for a couple different reasons. This is just too basic. The carbon-oxygen bond is too stable, and so this is not going to be the product, okay? This would simply be the product in that case. All right, what about this one? Let's see. How about just propane with potassium cyanide here? Can we get the cyanide on there? And let's see, what would be the leaving group? Oh, hydride would have to come off. Now, what do you think about that reaction? Is that going to work? Or are there going to be some problems there? How good of a leaving group is hydride? Just come on. Not very good, right? Its conjugate acid is hydrogen gas, which has a pKa of 35. Okay, so this is very basic to pull that off. Plus, a carbon-hydrogen bond is very stable. That's not a good leaving group, okay? The better leaving groups are these, right? Carbon-halogen bonds are relatively weak. Remember the bond dissociation energies? Those were down around 50, 60 kcals per mole, right? A carbon-hydrogen bond, anybody remember the bond dissociation energy of that, just roughly? Must be much higher, right? And what was it? It's around 100 kcals. You're not going to break that, okay? So this would not be the product. In fact, here you just get no reaction. Here you don't get the SN2, okay? You just get acid-base chemistry, okay? Because of that combination. It's a bad one, okay? Better leaving groups are the halides. Speaking of leaving groups, Here's one that actually involves a carbon-oxygen bond. We call this a tosylate. Don't worry, we'll define that later on. It's a sulfonate, you could say. It's related to sulfuric acid. You see the oxygens on sulfur and everything. This whole group, some of it we don't draw it out, it stands for paratoluene sulfonate. This is a toluene group, this methylbenzene. Don't worry about that naming yet either. We'll see that later. But the issue is, this can come off with a nucleophile. And here's acetate going on there. What would be the product? Acetate would go on and it would give us the ester product. And look, tosylate would come off. That's actually a good leaving group in this case. Why is this considered a good leaving group now? I thought I just said oxygen is a terrible leaving group. Well, hydroxide at least. But what's different now with tosylate? Now we have O- coming off, but what? This is coming from a strong acid. So this is a weak base coming off, right? And what do you see about the stability of the tosylate leaving group? It's resonance stabilized, right? So that actually turns out to be a very good leaving group. We sometimes call it a pseudo-halogen, meaning it acts like a halide leaving group. In nature, we have the phosphates, and that's another oxygen leaving group. A lot of things in biology get phosphorylated, we say, with kinase enzymes. And that can actually turn alcohols into good leaving groups. And it's a similar issue there. A nucleophile can come in, and then what? You have the stabilized phosphate anion, okay? So it all comes down to the stability of that leaving group anion. If it's not very stable, right? If it's, a strong base or whatever, or, something that's just from a very strong bond, it's not going to function as a good leaving group, okay? Questions on any of that? That kind of summarizes some things there. So leaving group, the first thing to look at is the X group here has to be what? A very weak base, okay? Has to come from a very strong acid, you could say. It's conjugate acid. But that's really a key idea there for that. Let's look at nucleophiles now. We have a whole bunch of nucleophiles. In fact, let's summarize all those together. Let's see, what type of nucleophiles, and again, this is for SN2 reactions, okay? And here, the key thing is usually they're charged, and they're small, okay? And their pKa's of their conjugate acids is about in the 5 to 15 range. That's usually the optimal range, okay? And also something about the size, how small they are. So a couple factors there. But we've already seen acetate, and sometimes we just abbreviate that ACO-, okay? Yeah, that's a good one. pK of acetic acid is what, 5? And it's relatively small. It's resonance stabilized, but it can function very good. It's charged. And what about charge? What do we mean there? Well, it has high electron density. And so when it collides with an electron deficient leaving group molecule, it pushes that leaving group off very well because it has excess electron density on it. So again, it's the collision and the speed of that collision that leads to an effective reaction. Okay, we'll see, details. We're adding that nucleophile into the sigma star of the carbon that has that leaving group. So we'll see the rest of it. But let's write down all the anions. Azide, N3-, is also a good leaving group, small. Cyanide, we've already seen that. Iodide can be a good nucleophile under some specific conditions. Normally think of halogens, as being outside this range. They're down in the minus range, right? But this big polarizable anion here under certain conditions, in particular with the polar product solvents, this can be a very good nucleophile. We'll talk about solvents too today in a couple spots. So what do we get? I-, okay. Sulfides, and the R means whatever R group, carbon group is on there. And we saw that last time, right? We made the skunk molecule. It can be hydrogen sulfide or an alkyl sulfide, okay, anion. So sulfur nucleophiles are actually very good. Oxygen nucleophiles, yeah, okay, so alkoxides. They're a little bit on the high range because the pK of alcohols is what? 15, 16, some are up around 18. That's a little bit too basic. A lot of times these will do E2 eliminations instead because they're a little too basic. These, hydrogen cyanide, hydrogen azide, those are 5 and 9. Those are perfect. They're right in this range, and they're very small there. Hydroxide also can be a good nucleophile. What else do we have? We had acetylene. We're adding a lot here, right? And then all the combinations with your leaving group, right? The different variations there. Oh, by the way, so, whatever the leaving group is here, primary reacts a lot faster than secondary, much, much faster than tertiary. In fact, we don't consider tertiary leaving groups as part of this grouping. Primary faster than secondary, so there's some kinetics there. And that has to do with how fast the nucleophile can attack, because it is a bimolecular reaction after all. So we've got acetylenes there. Oh, we should add ammonia, even though it's neutral. So here's our first neutral one. All these other ones are charged. But because it's a moderate electronegativity atom, 2.8 on the Pauling scale, neutral amines are good enough nucleophiles to do SN2 type reactions. And they can be substituted. You can have an alkyl group on the amine. So those, are SN2, and your rate here is what? Proportional to the starting material and the nucleophile. Okay, bimolecular. Now let's put a couple more up here to talk about other neutral nucleophiles like water and alcohols. Okay, so that's differentiating these two, and students often mix these up. Is the reagent alkoxide or hydroxide, or is it neutral water or an alcohol? Okay, if it's neutral here, and with a tertiary faster than secondary, much, much faster than primary, this is a different mechanism now. This is SN what? SN1. This is unimolecular, okay? The rate, the kinetics, is only proportional to the starting material because the rate limiting step or the slow step is the formation of the carbocation, okay? And that relates to the nucleophile, right? These are neutral now. They're not negatively charged. They're not bringing it on when they collide. They don't have high electron density like the negatively charged anion reagents. They're neutral, okay? So they actually wait around until this just ionizes, okay? And these are polar solvents. We often call these solvolysis reactions, okay? So, yeah. The other thing we need to get into is right here. With SN2, with a secondary, S stereocenter goes to R, and R stereocenter goes to S. That's more evidence of the bimolecular reaction, the stereochemistry. So I think that summarizes it, shows you the different nucleophiles and what goes on. Oh, one other thing to say here. This one right here. Sterics can play a role. Now, what do we mean by sterics? That's a term we've used a couple times. I think we've mentioned it. What does sterics refer to when we talk about a molecule? Yeah, the size. So how big that thing is. So RO minus here can be something small like methoxide. Okay, and that fits into the paradigm here. Generally, small nucleophiles are best for SN2. But what about this one? How about T-butoxide? If you have a tert-butyl group on there, that's a very large group, right? It's branched. Those 3 methyl groups make it very large. This one will do SN2 just fine. This one here always does what? E2. And that's chapter 8 coming up. But I like to point that out early on when we discuss all the nucleophiles here. So that's one thing to keep track of. Sterics can play a significant role. But if you look at most of these, they are small overall in size. Okay, solvent. Well, yeah, let's mention solvent. Maybe we'll just go to the overhead here, Colin. Well, let's see. So we've already shown this panel, I think, talking about leaving groups. And we mentioned OH coming off here. But if you protonate an alcohol and form the hydronium ion, that can be a good leaving group. And we'll see that later on when we get to some alcohol reactions. But if this is just ROH, that's a terrible leaving group, okay? Because then we're generating hydroxide, okay, which is too basic and not a good leaving group, okay? But you see the halides here, all of those coming off. pKa's are all low there, but a hydronium ion does fit into it. We can make alcohols reactive toward nucleophilic and elimination reactions. But again, we almost do it always under acidic conditions and make them hydronium ions. So here are the bad leaving groups. Well, we already mentioned OH. There it is. Came off as hydroxide. You see the conjugate acid would be water. That's 15. It's way higher than the halides, right? Well, there's a halide, fluoride. There's a couple things there. It is on the more basic side when fluoride comes off. The pK of HF is 3. And also, what's not shown here is the stability of these bonds. A carbon-fluorine bond, being a small atom, is very high in bond dissociation energy, over 100 kcals per mole. So that's a bad leaving group compared to chloride, bromide, iodide, whatever. Also, an amine, that's a bad leaving group because that would be, what, amide? Hydride, we showed that. No reaction for that one, right? Way high. I'm breaking a carbon-carbon bond under SN2 condition. That won't work. Okay. So, yeah, I think that goes along there. Solvent effects. Now, there is charge separation in all these transition states. So if you have a more polar solvent, that will tend to stabilize the transition state and lower its energy and make it faster. So in general, polar solvents increase the rates of both SN2 and SN1 type reactions. And why do we need to use a solvent anyway? It seems like a waste. It doesn't really participate directly in the reaction. What's a solvent there for? What can you say about that? It's a liquid solution, which is more convenient to handle, you could say. It's also a thermodynamic sink, you could say. It absorbs energy. Some reactions are very exothermic. They can generate a tremendous amount of heat. The solvent helps absorb some of that heat. What else about a solvent? It's polar enough to bring the polar nucleophiles into solution, right? So these are polar salts, most of them. You need to have a polar enough solvent just to bring them in contact. So there's a lot of practical issues there. There's two types of solvents. We have the polar protic solvents, water, alcohols, I've already shown those. Oh, and carboxylic acids. These are all typical polar protic solvents. Why do we say protic? Because they can hydrogen bond, both hydrogen bond donors and acceptors. There's lone pairs that can function as acceptors of hydrogen bonds, and also hydrogen bond donors. There are hydrogens on oxygen here. Yeah, amines can function as polar protic solvents as well, but they have a significant odor. They're difficult to get rid of. Alcohols are perfect for polar protic solvents in industry. And what do? They solvate both the cationic part of a reagent. So here's the reagent. Bromide, that's a bad leaving or bad nucleophile. So you can picture any of these other anions in here being solvated by the positive end of a polar protic solvent. Okay. Yeah, so that's, I think, all we need there. And then the polar aprotic solvents actually work best for SN2 reactions because they selectively solvate the cation part of a reagent, and they don't solvate the anionic part very well. The partially positive end of a polar aprotic, there's no OH groups here now, but these are polar molecules. The most typical ones are THF right here, the cyclic ether, and acetone. Some of the other ones you might be familiar with, DMSO, dimethyl sulfoxide, or DMF. Acetonitrile is kind of toxic, so is HMPA. We avoid those. THF is really the workhorse, or acetone here. And you see the negative end here can help bring the cation part into solution. But they don't solvate the anion very well. They leave that more exposed, and it can collide better with the substrate and then make the SN2 reactions go much faster. I'll show you some actual numbers later on for that. The halides are very weak nucleophiles, but if you use a polar protic solvent like this, actually iodide is the best anion in that case. It has to do with the large iodide anion not being solvated very well because it's so large. It's polarizable. It leaves it available to be a nucleophile. But in aprotic solvents, fluoride, if you look at the halogen series, F minus turns out to be a better nucleophile. And that parallels basicity. Nucleophilicity always parallels basicity. The more basic a reagent is, the more charged it is, it's generally more nucleophilic. I think that's all we need to say about that. Here's all our nucleophiles again from your book. Yeah, the key thing to look at is the charge here versus water there. Yeah, okay. You can also compare oxygen nucleophiles versus nitrogen nucleophiles. These two should be moved over here. Well, this is the charge region. These two right here can do the SN2. Why? Because they're less electronegative than oxygen. This lone pair is not held as close as oxygen is. Okay, so these can be good SN2 nucleophiles. Okay, yeah, so let's get into the details of the mechanism now. And I like to put on the board a couple of key reactions. So let's go back to the board here, Colin, and look at the two key reactions and list what we know about the mechanism and what are the key hallmarks of SN2 versus SN1. So here we've got methyl bromide plus sodium acetate, okay? And we're going to methyl acetate, okay? We're making that ester plus sodium bromide, okay? So what do we know about this reaction experimentally? Well, we can observe the rate. And the rate is proportional to both methyl bromide, okay? So if you increase the concentration of methyl bromide, you increase the rate. If you double the molarity of methyl bromide, you double the rate, okay? The solvent in this case will have THF, okay? And if you double the rate of sodium acetate, ACON, you'll also double the rate. If you double both of them, it'll be 4 times faster, okay? So that's something fundamental about the reaction. This is called the molecularity. Because it depends on 2 things here, we call it bimolecular, okay? And it is a substitution reaction. What got substituted? The bromide came off here and the acetate went on there. So that's the bond we just made there, right? So this substitution is bimolecular and it involved a reagent that's nucleophilic. So that's where the whole thing SN2 comes from, okay? Just looking at the molecularity of the reaction. Now, overall, this is a very small R group here. If you look at the kinetics with a wider range of substrates, primaries are always faster than secondaries, much, much faster than tertiaries, okay? So that tells us quite a lot about the reaction. Let's compare this to another type of bromide, tert-butyl bromide, okay? Same reagent. Let's use sodium acetate again. And we do get the tert-butyl acetate product. That tert-butyl's still there. That's that same bond we made right there. But if we look at the rate here, the rate only depends on the concentration of the tert-butyl bromide. It's independent of the concentration of sodium acetate. We can double the concentration of sodium acetate. That'll have no effect on the rate in this case. So its molecularity is unimolecular, okay? But it is still a substitution. And it involves a nucleophile that's actually charged in this case. It's a relatively weak base nucleophile, and this is why this works in this case. If this was more basic, we'd get an elimination reaction. We'll see that in chapter 8. But this is, pK of 5, so it's on that low end. And it is unimolecular. So we changed the designation here. We call it substitution nucleophilic unimolecular for the 1 there, okay? How can we come up with a mechanism that's going to be consistent with this data? And that's what we're doing. We're coming up with a theory for what our mechanism is going to look like. The other thing here is if this is a stereocenter, it is inverted. If this, at R or S, whatever, Bimolecular attack at that position. There's that inversion of stereochemistry that I mentioned before. So we'll have to accommodate that in our mechanism also. So let's see what we need to do here. What's it going to look like? Well, let's come up with a mechanism for this. So there's a number of mechanisms we could consider. Direct attack, an associative thing via a hypervalent carbon. We could picture all sorts of different approaches to the mechanism. I'm just going to emphasize the one that we know to be the true mechanism. You can consider some others. We could like deprotonate, take a proton off first, and then lose bromide, form a carbene intermediate. There's all sorts of crazy things we could imagine for this, and these were all considered early on. But all the data is consistent with what I'm going to show you now, okay? So it just involves taking the nucleophile, okay, and looking at this bond right here. That is a sigma bond, but it also has a sigma star bond on the back of that carbon. That's the empty orbital. The sigma bond is where the electrons are, right? They're spin paired. The empty orbital is the higher molecular orbital, the sigma star. Remember we drew those diagrams before? Here's our nucleophile with the high electron density. And it has a highest occupied molecular orbital where these lone pairs are. There's 3 of them. Let's just take one and dump it over here into the sigma star. Now when you fill into the sigma star, what does that do to the sigma bond? It's going to weaken it, and it's going to push these electrons off. In fact, it's going to happen all at the same time. We say it's concerted. Okay, in this concerted mechanism, we have bond making happening at the same time as bond breaking. Okay, and what's that going to look like? There's going to be, 5 bonds to carbon now? That's going to look kind of crazy. Let's combine this with the stereochemistry idea right away. Let's do this molecule, which is a ethyl group, you could say, but we've got deuterium and hydrogen here, and we have a stereocenter. This is a primary molecule, but it is chiral because it has the 4 different groups. So deuterium, remember, is the heavier isotope of hydrogen. These have been made before, these chiral primary leaving groups. And let's do that with acetate and see what we get here. It's got to be the charged one here. And what do we get? We get this. Okay, and that can be measured very carefully. Let's keep track of R and S here just to make sure. So here's our lowest priority group, top priority, second, third. Deuterium does have higher priority over hydrogen. So what is that? That's indeed R. Yeah. And then here, what do we have? Top priority is the oxygen, right? Yep. And that one's R. Okay. And you see the hydrogen was in the front here, and now it's in the back, and that's right there. Okay. So how does this go here? What are we talking about? Let's look at the transition state. So we have our bromide. We have hydrogen here. We have deuterium coming out, and we have methyl going back. Okay. That's still R. Yep. I just redrew it a little bit differently. And let's take acetate here. And let's go ahead and attack that sigma star. There it is right on the back of that orbital. Now let's fill it in there as we begin to take that off. And so now we can draw an intermediate point. Let's draw the transition state. So we'll have the deuterium, the methyl, the bromide, and the acetate all on there. Now, some of you say, wait a minute, Dr. Andrus, you drew 5 bonds to carbon. That obviously violates what? The octet rule. Okay, but these aren't full bonds. Okay, maybe we draw these as dashes. Okay. And what we have partially negative here now and partially negative there. And, our carbon right there is always partially positive. So here's our transition state. our double dagger, our intermediate there, and we'll go back to the overhead in a second. But you can see as we do that, let's just follow this through, and then you flop these atoms over a little more, and then you go directly to this. Okay, you can see that hydrogen's back there, the methyl group back there, and the oxygen right here, and then you can assign your R thing. Go ahead and do that. You can already see it kind of coming out right here already, right? With that off there, there's your R or your R rotation. Let's see, it should be S. Sorry. Yeah. Yeah, thank you. Who said that? Okay, yeah, very good. Okay, yeah, this is S. This one's R. Let's verify that. Let's start over. Yeah, 1, 2, 3. Okay, yeah, that one's R. And which one's this? Yeah, good thing I checked that. Top part, second part. Yeah, so that's rotating this way. You can see it right here, right? 1, 2, 3. Yeah, with that in the back now, with this coming off. Okay. So this transition state is bimolecular. The collision involves this guy, the substrate, the starting material, and our nucleophile. So that should be the slow step. That's where the molecularity of the reaction is borne out, right? Right there. Let's look at a couple other examples of this, so we'll go to the board. And I do have the model. I have the dreaded SN2 machine right here, a little bit of heavy metal involved. In fact, this comes from a cymbal stand from a drum set, so it really is heavy metal. Yeah, the guy pounded on it, and I think the stand fell apart, but I still found it useful to illustrate the SN2 reactions. We'll use it here in a second, I don't know. Well, let's look at a typical secondary halide. Here's an iodide. Draw the stereochemistry in there, and let's react it with sodium sulfide. We could react it with any one of these nucleophiles, right? Here we're in acetone, our polar aprotic solvent, which you can selectively solvate the cation and leave the sulfide more available for attack. It increases the rate of the reaction, helps stabilize that polar transition state between the two, and gets this into solution. That's a salt after all. So you couldn't use like hexanes or propane for a solvent, right? Because those are non-polar, benzene. It wouldn't bring these guys together, okay? This one's non-polar. That would go into hexane. But this will go into acetone. Acetone's kind of moderate polarity, and that's a good thing to bring the two together. And what's our product here? Well, it is the sulfide. We're going to have to invert the stereochemistry. So that's a convenient thing. If it's a secondary stereocenter and it's up right here, just make sure you put your nucleophile down, okay? Well, let's compare RNS, top priority, second, third. So what one is this? Is that indeed S? Somebody double check that for me again. I've already messed up one of them today. Okay, and then what's this one? Yeah, that's R. Okay, you should be able to see that, combine that. So if it's just a primary position, you don't have deuteria here. If it's just two hydrogens, then it's not a stereocenter. You don't need to worry about it, okay? The secondary ones is where it's critical there for that. And what would we do for the transition state? We kind of have this propyl group on there. We have the methyl group coming out. Hydrogen in the back, maybe. Iodide on there, and sulfur on there. And again, this is the partial negative. So these aren't true bonds there. They're starting to make that bond and starting to break that bond. And you see we invert that. Because of the backside attack here, we flop over all three other groups on the carbon. Okay, it's called Walden inversion for Walden, the physical chemist who developed this theory. Or it's kind of an umbrella effect. If you have an umbrella in a windstorm and it picks up, you can flop the umbrella over to the other side. And that's what we're going to do with the machine too to verify that. But as that goes on and this comes off, I think you can see that that's going to be the S or the R now. Yeah, you can verify that. Go through that with models carefully. Need to. One other example here before we do the machine and some other stuff. How about a cyclic one? Yeah. So here we've got the cis bromo methyl cyclohexane. And let's do this with sodium cyanide. And what's the reaction? Well, it's secondary. So these are slower than primary ones that we've seen before. Secondary will be slower. But this, is that a stereocenter? See, it's not really a stereocenter. But we've got the cis versus trans geometry isomers, right? Stereo isomers that way, okay? It doesn't have to be chiral. It has this relative stereochemistry. This is cis, so what's the product going to be? Well, we need to invert that center, right? So we've got hydrogen here. So cyanide's going to come from the bottom and push that bromide off. And what that effectively does is it pushes this hydrogen up, right? So our hydrogen will be up right there. Cyanide will be down relative to this methyl. And that's the only thing. We're comparing the relative stereochemistry to the methyl, right? So what do you call this? It's not cis anymore. This is indeed the trans stereoisomeric product, okay? And again, we're inverting the center, even though we can't assign RRS here, okay? But we can assign that relative stereochemistry. All right, let's do the SM2 machine here. See if this is going to work. Yeah, we got some time. Very good. And I might need some help here. I might need a couple volunteers if you feel like you can relate to the heavy metal drum stand here. Feel free. I might need your help. In fact, I think need 2 volunteers. Now let's see the reaction here that we're talking about. It's got a benzene and a bromide and a methyl and a hydrogen. And we're reacting it with sodium hydroxide. Now that's a pretty basic nucleophile, but it is good. And under the right conditions, we can get this product. And there I've kind of emphasized, exchanging the hydrogen and the methyl. And that's okay. Let's see if we assign RRS to the stereocenter here. Top priority, secondary, third should be R. And then what about this one here? We've got top priority. So, we got to hold that in the back or look on the back of this, right? So what is that? That's S. Yeah. Okay. So I think that's it. Yeah, good. SN2 reaction. Let's look at the transition state here. We've got bromide, methyl coming out, hydrogen in the back, and phenyl. And we're going to color code these. Let's see. Gotta flip it around. Our nucleophile. Oh, it's already falling apart. I knew it. Okay. Yeah, where'd it go? There we are. So let's see. What have we got? Oh, went way over here. My nucleophile's escaping. Let's see. Okay. Let's see. So we've got a couple groups on here. We've got a green leaving group. And we've got purple for the hydrogen, I think. Orange for the methyl. Then let's see, yellow for that. Yeah. And our nucleophile is going to be hydroxide coming in from this side. There we go. And that's going to be red. Okay. Well, let's draw the product here. We're going to have OH, methyl, hydrogen, and phenyl. Okay. Should be the same as that one, right? I think I just redrew it. Yeah, that's still S. Okay. Just flip it around. I think, yeah, it's the same thing there if you just rotate that around. Sorry, I keep drawing it differently. It's so we can orient the machine here. We'll have red and then all these other colors here, what orange, purple, and yellow. Okay. So let's make sure we got this right. So we've got orange up there, right? Okay, green's coming off there. We've got purple in the back. Let's see. Do we need to change that one? We got yellow down here. Oh, let's change orange and purple. Have we got that oriented correctly now? Can I have a couple volunteers come up and help me out? Come on up, guys. Let's see. Don't be shy. Please, come on up. There we go. Come on up. I think we'll need two, actually. We'll kind of orient toward the camera here. So we've got this orientation, right? We've got orange, yellow down, purple in the back, and what do we have? Green here coming out. Come on over here. You might get in the way of the camera. But yeah, you're actually step over here. Let's try to orient. Okay, we see some stereochemistry there. Okay, now take the nucleophile in your hand there, and that's the red coming in. Okay. And go ahead and attack. Okay. And stop at that point. And what do we have right now? We have the transition state. We have the 5 things bonded there. And notice the 3 that are not reacting have adopted a plane. You could call this trigonal planar geometry, right? For the 3 groups in the plane. What? Orange, purple, and yellow. Okay, keep pushing in the nucleophile. There you go. Push it, push it. There you go. Look at that. Okay. Yeah, it really made an impact there. So what do we got? Red here. We've got orange here coming out at you. Purple in the back. Yep. And yellow right there. Okay. So maybe we could go back the other way. Let's reverse the SN2. Push it in the backside. Keep pushing. Keep pushing. Okay. There we go. Okay. And this is pretty corny, right? Somebody's drum stand who fell apart. But it's got the 3 groups here, and then that. Okay, let's go in the forward direction again, see if we can make sure this works. There you go. Keep pushing. There you go. Oh, okay. And we've gone back to sp3 hybridized, right? So we kind of temporarily rehybridize in the transition state, that trigonal planar arrangement, but it really works there. All right, let's give our volunteer a round of applause there, helping us out there. Now, I know this is kind of corny, watch the video again if you need to relate it to this, but we'll go to the board here and check it out. And also in ChemTube, you've got, bunch of good examples there that are animated. You can see the 3D things and rotate them around to make sure you can see what's going on. So here we got the one we drew on the board to begin with, which is just what? Methyl bromide and acetate. And yeah, it's bimolecular. There's the transition state. Just involves the collision, the backside attack, we say. It's still going backside attack, even though there's no stereochemistry there, and we don't need to worry about it with the primary generally. But it is inverting, okay? That's consistent with everything we know about the data, especially more modern MO theory, the HOMO-LUMO. You should know what the HOMO is in this case. That's the nucleophile. And the LUMO is what? The unoccupied orbital is what? The sigma star, okay? It's right there, okay? There's the charges going down the transition state. Okay, here's the thing I mentioned about the increasing rates for primary faster than secondary. Why is that? Well, that backside attack is more hindered if you have a more substituted leaving group. Tertiary, very slow, okay? And so what do we got here? Methyl, very fast because there's nothing else on the carbon to hinder it sterically. Primary here, secondary, tertiary, being the very slow end over here. So it's increasing right to left, as it's shown here. Increasing hindrance, left to right. Tert-butyl being the most hindered, and here's the transition states, right? The nucleophile, the backside attack here is fine on a methyl. It's unencumbered. A primary is okay, it's just got the one other carbon there. Okay, it can still hit the back of that and get to that sigma star. Imagine where that sigma star is. It's right here, right, where the nucleophile is filling in. And then secondary, wow, we've got 2 alkyl groups now pointing right back, parallel toward that sigma star. That's going to really slow this reaction down, okay? So these reactions with the secondary that we've been shown, those take hours to go sometimes, okay? The primary ones are done in minutes or even seconds. They can be very fast, okay? And then tertiary can be on a geological time scale, years, eons. I'll show you some actual kinetic data, some actual numbers at the end of chapter 8, but that'll be more clear. But But you can see just from that, is that clear though? If it's not sterically hindered, we say, the approach of the nucleophile to the sigma star is unencumbered and will be relatively fast, whereas a secondary will be slowed down in that case. Okay. Yeah, so here's the transition state of a typical one that's going to be lower in energy, you see. And here's a tertiary one, which would be very high. In fact, this will go a different type of mechanism. This will do an E2 reaction because the SN2 is withdrawn here. What they're emphasizing here is this transition state's a lot lower for the methyl leaving group versus this one, tert-butyl, is very high. Okay, that's all they're emphasizing there. And I wanted to show you some applications of SN2 reactions, why they're important. Here's a drug, ethambutol, which is an antibacterial agent. It's made via this amine alcohol. And you can kind of compare the nucleophilicity of amines and alcohols, right? Alcohols have 2 lone pairs. Why is that not the nucleophile? Well, it's more electronegative. Those lone pairs are held close to that oxygen. Whereas the less electronegative nitrogen is the better nucleophile, even though it's neutral. And if you add 2 equivalents of that amine in with this dichloride, you can get the drug directly there in high yield. Okay, the solvent would be THF in this case. Here's another common drug, Prozac, the antidepressant agent. Here's a primary iodide. That's a great SN2 reactive partner. Okay, and here's a good nucleophile, the methylamine. And yeah, that reaction right there can go to put that in. There's another reaction that has to go to put that trifluoromethylphenyl group on. So that's not shown there. But this right here, these red bonds, they're emphasizing the SN2 applications. Here's another one. I mentioned Ceravent before. It's this long-acting asthma drug, beta-adrenergic receptor agonist. And you can see a couple SN2 reactions. There's the alkoxide with the bromide right there. And here's an amine with that primary bromide to put that bond in place. So I'm not drawing, color coding the bonds that are made here. You kind of have to look through it and figure it out. And then right here, you react this compound 4 is right here. And that's another SN2 reaction right there to put that other group on the amine. And then the salt form is what's actually delivered as the drug there. Here's the one in nature. It's a sulfonium group called SAM, S-adenosylmethionine. It's an unusual leaving group, but you can imagine this whole part down here is the leaving group. Here's the alkyl group that remains on the nucleophile. You can kind of look through that. There's an important application here in neurotransmitters, norepinephrine, noradrenaline versus adrenaline. Those act in different sites of the body for the fight or flight response, ramping up the body to do work under stress there. And noradrenaline is converted into adrenaline just by putting a methyl group on that amine right there. And it does it via SAM. So there's the SN2 reaction showing. And this is a leaving group, the sulfonium group. That's different in nature, okay? They usually use phosphates or sulfoniums to do that kind of stuff. And I think that's it. We'll look at SN1 next time and finish it off. So make sure you're read up through the whole chapter there, 7. And getting ready to do the homework and the quiz. All you need are the SN2 reactions, I think, for the quiz. So we'll finish there. Thank you. We'll see you next time.